So first of all, thanks to the organizers, Shudhir, Biplab, Genevieve, Fauzi and Justin and others. And it's really very different right now here, because all the other times, previous times I was here, the laughter of Rohini, the scientific discussions with her and her questions and comments, I mean those are really something, and I really miss them. And this talk is a tribute to Rohini from my side. I had the good fortune to work with her in the very recent years, starting from 2019 onwards. Of course, she was a teacher, and I came here long back, like for some talks or something, 2010, 2011, 12. And of course, got scolded by Rohini. I think many of us got scolded by Rohini at some point or other. But starting from 2019, I collaborated with her. We wrote quite a few papers. And I think because Higgs and dark matter, they are very special to Rohini. So I chose these two papers with Rohini, Genevieve and others, where the primary motivation was, so these two are of course in the context of two different models, but the main connection was that how the BSM Higgs sector is actually coupled to the dark matter or can contribute to the dark matter production and also the dark matter indirect detection, and of course there were details of collider studies as well. So I don't need to remind the audience about this. We know that there are different production mechanisms for the dark matter. There are different proposals. The most popular was WIMP, but also FIMP, and then very recently all the other proposals which I have not listed here, like conversion driven freeze out, and those things one can also realize. So I will just straight away come to the model, and this is one of the models which is actually non-SUSY models, where we collaborated. So we actually do not have any paper on SUSY. I do not have any paper on supersymmetric models with Rohini. All my 3 papers that I did on non-supersymmetric models, and this was one of them. So here in this model we have this gauge singlet neutrino field and also SU2 triplet fermionic field. And what was the motivation? Because simply we know that we were thinking in the context of seesaw, particularly type 3 seesaw. So if you are familiar with the neutrino mass models, you know type 3 seesaw kind of model is a very popular neutrino mass model. And we were just thinking that, so if we just have a SU2 triplet fermion in our model, then whether that can be a dark matter candidate. And as we know that in a majority of the parameter space, it's actually kind of underabundant. And then if we consider some other tweaking of the model by this gauge singlet field and some BSM Higgs fields, then how the phenomenology basically changes. So this was sort of the motivation. This is a scalar triplet field, this was a fermion triplet field, this is a gauge singlet field, and this triplet scalar, it's a real triplet, it acquires vacuum expectation value. So in this model, the Higgs spectrum is that there are presence of this CP even neutral Higgs, the charged Higgs, and for simplicity we consider that the mixing in the neutral Higgs sector is same as the charged Higgs sector. In the dark matter part, we have, this is the rho and n. Rho and n, these are the mass eigenstates, and either of them can be the dark matter candidate. And what we wanted to see that, so this term is actually important. This is the term which connects the triplet fermion with the gauge singlet fermion and the triplet Higgs. And we just wanted to see if we just have a very small coupling, just a very small interaction between these different fields, what kind of phenomenology we can expect. So keeping this in mind, we looked into the possibility where this y rho delta, that was the interaction term between these fields, it's extremely tiny, around 10 to the power minus 10 to 10 to the power minus 12. And in this range, life is very simple. So this rho is primarily triplet-like state, and this n is primarily singlet-like state. And then what you have, depending on the mass hierarchy, you can have either rho is a dark matter or n is the dark matter. So now, if I look into the dark matter production in this kind of setup and just categorize this. So one possibility is rho is the lightest, rho is the dark matter. The other possibility is n is the lightest, n is the dark matter. But there is one difference. This rho is a SU2 triplet, so it will be a WIMP kind of scenario, and this n, it's a standard model gauge singlet. On the top of it you have a very small Yukawa interaction, so it will be primarily, it's actually the FIM kind of dark matter scenario. And here, because for the rho, always there will be these channels, so rho to bath particle will be there, but there can be significant contribution from the BSM Higgs sector. So I will just summarize this and then I will go one by one. So here what is happening, this BSM Higgs is decaying to n rho, and it's building up the abundance of n, and the late decay of n, a very late decay of n, can actually give significant contribution to the relic abundance of rho. In this scenario, which is a fusion dominated scenario, the two bath particles can produce n, and then n can decay to rho and a BSM Higgs. And if n is the dark matter one, this is decay dominated, which essentially implies, so n is the dark matter, and that's a non-thermal dark matter, so it's a freeze-in kind of scenario. So the BSM Higgs can build up the abundance of n, and as well as the late decay contribution from rho can also help to acquire the correct relic density. And then there are fourth possibility, which is itself the annihilation channel, bath particle to rho n, can substantially contribute to the relic abundance. So let's first look the first one, where rho is the dark matter candidate. So all of these channels will be present, and we know that just if we look into the perturbative calculation, then if m rho is less than around 2.4 TeV, then in a majority of the parameter space you actually get the underabundant dark matter. Now from the lower side, we also have very tight constraints on this m rho from the collider search, disappearing track searches, because rho is a triplet, rho has a rho plus minus rho 0, so a rho plus minus can give rise decay to rho 0, and it can also produce a pion, and this pion is soft, so you can have disappearing track searches. This can give a tight constraint. So with this in mind, we look into this possibility. So here what is happening, that n is produced from the BSM Higgs. N is a non-thermal particle, and once n is produced, then the decay of n into rho h1, it can compensate the underabundant dark matter, what was required to compensate the relic abundance. So this is happening here. So here we can see that for the m rho, this is the omega rho, this is actually underabundant, this is the production of n from the BSM Higgs decay, and then this is the late decay of n, that is actually giving rise to substantial contribution towards rho abundance, and you can acquire the relic abundance. The second possibility is where n is the dark matter. So here this is the freeze-in scenario, this is the thermal freeze-in, this H2, H plus minus, they were in thermal equilibrium, and they give rise to n rho, but the rho itself can also give substantial contribution through late decay. So this rho going to NH1 can also substantially contribute to the relic abundance of n. So this is the thermal freezing part, and this is this non-thermal or late decay contribution of rho, and together you can satisfy the relic density. But in all of this scenario, what is happening, that the moment you have H2, the BSM Higgs is decaying to rho n, because on rho you have a tight constraint from the collider. So in some sense your BSM Higgs also needs to be heavy, at least few TeV, and then what is happening, that is out of reach of the collider. So then we ask the question, so this is purely Rohini and Genevieve, they were persistent that we have to look into this possibility that the light Higgs, whether you can have a light Higgs kind of scenario. So the main key aspect is that these decay, you need to work in some other kinematic range, so parameter space, where these decay is actually forbidden. So we looked into two possibilities. One is where 2 to 1, 1 to 2 dominated scenario, and the other is 2 to 2 dominated scenario. So what I mean by that, this is the 2 to 1 and 1 to 2. So what is happening, that N here is produced on shell from the fusion process, and then later N have a late decay to rho this H2 or H1, and here this is the mass of neutrino, this Mn versus the required Yukawa, and the color bar represents the BSM Higgs, and all of these points they satisfy the relic abundance, and as well as the Big Bang nucleosynthesis constraint, because N decays very late and we are considering the coupling to be 10 to the power minus 10 minus 11. So of course the question is whether they can jeopardize the BBN, the Big Bang nucleosynthesis. And as we can see that in for the MH2 mass, let's say few hundred GeV, 200, 400 GeV, I mean you have sufficient amount of points, but the BSM Higgs is a light, which is good, because then you can look into the possibility how it can be probed at collider, and you can satisfy the relic density. The fourth possibility, so in this case the rho was the dark matter. The fourth possibility was where N is again the dark matter, and we asked the question that just 2 to 2 annihilation kind of things can give substantial contribution from the bath particle itself. So this is the other than the standard freezing and decay, this rho going to NH2, now this substantial annihilation contribution is also possible. So this is M rho versus MH2, and these are the points where, I mean, the decay contribution is, here it's almost 100% or 70 to 100%. These blue lines are where decay contribution is 60 to 70%, and here this part it's actually can be a bit low, so it can be 50 to 60% and so on, and your annihilation contribution starts dominating. Now very interestingly and different from what we have explored before, so in general this film kind of scenario where you have a very small Yukawa, you cannot, it's very difficult, I mean you cannot probe it in the experiments like at collider experiments or something. But here what is happening, so this is the production cross section of rho plus minus or rho plus minus rho 0, and this is the lifetime of rho 0. So rho 0 was actually decaying to N and BSM Higgs, and BSM Higgs are quite light. So all these points, this is again the relic density is satisfied, and this line is the sensitivity reach of Mathusla, and this mass of N, contrary to all the previous scenario, they can be in the sub GeV range, and what we find that a significant amount of points are within the sensitivity reach of Mathusla. So you can actually probe rho 0 decay. Not only that, you can also probe this kind of Yukawa coupling. Okay, and then because again here the BSM Higgs sector was quite light, we asked the question that whether what will be the signature of this BSM Higgs, the neutral one and the charged one, and this was one of the, of course in our paper, I mean we could not pursue this in detail, but this was one of the proposal that we were discussing with Rohini and Genevieve and others, and hopefully we will pursue. Now in the remaining time that I have, I just want to discuss the last paper that I wrote with her, and just a few of the slides I have. So if I have 2-3 minutes more. So this is on Georgi-Makachek model, and this model personally I have never worked before, and it's a very complicated model with lots and lots of Higgs. So those who do not know, so there are 5-plate Higgs with mass MH5, triplet states with mass MH3, and then there is standard model Higgs and the custodial singlet BSM Higgs, and the other parameters are there, the mixing in the neutral Higgs and the charged Higgs sector. And we also looked the possibility, so we considered this model where this, on the top of this Georgi-Makachek model you have now a gauge singlet scalar particle S, and this potential is important because all the dark matter phenomenology is governed by only these two coupling. So this lambda A coupling is the coupling which it governs the interaction of this dark matter with the standard model Higgs, and lambda b is the one which governs the interaction of this dark matter with this all these 5 plates or triplet kind of states. And we looked into the possibility of the decoupling limit, and for a small v chi what happens. And this is a long paper, there are discussions on the unity constraints and so on. I will a standard model Higgs signal strength, but I will focus on only 2 of the BSM Higgs and the dark matter part. So type 2 seesaw, all the searches, for example, the type 2 seesaw kind of model has a doubly charged Higgs, and Atlas was and CMS also looking for this kind of searches where you produce the doubly charged Higgs and the doubly charged Higgs decays to same sign gauge boson. This is a very interesting signature, and this is the limit from Atlas. So this is the mass of the doubly charged Higgs, and this is the sigma times branching. Now, in how we reinterpreted this in our model, so other than the doubly charged Higgs, there are also other decay modes present. So, for example, H5 double plus can decay to a triplet and the gauge boson and so on and so forth. And this plane, so here all this is the along the y axis is the mass of the triplet states, this is the 5 plate, and here the triplet wave, and this is the piece which is missing after we put the constraints from this Atlas search. And what is happening here, so the mass of the doubly charged, the 5 plate and the triplet, they are becoming very similar, so they are nearly degenerate, and then you have almost 100% decay. This H5 double plus going to W plus is happening, and therefore it is actually very strongly constrained. The second one, that this H50 or the H, it can also decay to diphoton, and this branching can be large for a small this triplet wave. And again, this is a search from Atlas. This is the fiducial cross section times branching versus mass of this resonance. This Atlas search, they looked into different kind of production channels. One of them was this proton-proton to the production of this X, this resonance along with the gauge boson, and then X decaying to diphoton. Now, this analysis is important because not only this narrow width, but also they have lots of data and all the limits. I mean, the width dependent limit is also provided in their HAPE data. So if one wants to do or pursue some analysis, they can actually do it. So in our case, in our scenario, in all the parameter space, it was not a narrow width. We have lots of variation in terms of width, so we considered this limit, but also the width dependent limit that's provided in the HAPE data, and did a reinterpretation study. And not only this, we also had different kind of production modes. There are a number of production modes, production of X in association with the H5 or in association with H3. So the CART efficiency was also very different. And again, so we can see this is the allowed parameter space from the theory constraint, SM Higgs diphoton, doubly charged Higgs, the BSM resonance to diphoton. Now for all these allowed points, we pursued a study how much the contribution would be in the Rayleigh abundance. So the SS, this dark matter annihilation to BSM Higgs sector can actually be quite important if you have the corresponding coupling lambda b large. And so from this plot also you can see that the BSM, the annihilation into BSM Higgs is actually large, and this BSM Higgs can decay to diphoton. So you can have a very interesting signal, the gamma ray signal. So when lambda b is large, then you can actually have this kind of kink, and this is happening because there is more high energy photons are there above 100 GeV, so you get a kink kind of scenario. So in this plot what we did, so this was the Fermi-Lat limit, and this is the CTA limit. So for our case, it's not the W plus, W minus or BB bar, rather the BSM Higgs, channel to BSM Higgs is sort of like more relevant. So we basically rederive this CTA limit using the prescription given in this paper. And for the variation of the parameter space, we see that there are sufficient number of points where actually we have good sensitivity for CTA. In the summary, I think I have written many things, but the main message that I wanted to convey that the BSM Higgs sector can have a large role to play in the dark matter production. And I just want to share this slide. So the first work that I did with Rohini is actually on left-right symmetric model. So I do not know if Rohini had any other paper on left-right symmetric model, but certainly whenever I discussed with her, she was very interested in all the neutrino mass models, and which is very close to my heart. And this was the second work. Yeah, is it? Yeah, okay. Oh, okay. So this was some other paper. And this is the last paper, and of course we collaborated in the French CEFIPRA project. And this one I would mention, so this is, I was visiting LAPTH during the last summer, and this photograph is from there. We had lots of fun. We were discussing physics, and then we went to the hike, some hike also. And this paper I would mention because it was a long project. It took almost more than 1.5 years or close to 2 years, and it was very difficult for me at some point to keep patience. There was a deadline. Our project, CEFIPRA project, was about to end, and of course the students have put lots of efforts, right? And it will be nice if this paper come out within the project deadline. And this is something that have been possible because of Rohini. So the day she was there, the whole week, she and Genevieve, they actually went into modifying the draft and text and everything. And the day when the students submitted the paper on archive, I was actually flying back, and they did give the positive signal to the students that please go ahead and publish this paper. And I'm really, really very thankful to Rohini. So not only for this, but of course, whenever we had discussions, it was so much encouraging and the inspirational. I just want to thank Rohini for her support, her encouragement, and for being such an inspiration to all of us and to me. So thank you.